So last time we discussed strap footings, and strap footings are used when you have eccentric footing, eccentrically loaded footing on the boundary, and we have an inner column which is more heavily loaded. So by having a fairly rigid beam between those two, we'll be able to induce some hogging action in the connecting beam due to this beam trying to prevent the rotation of the outer footing. So we can actually design the beam to resist some bending moment, so that part of the load to be resisted by the outer footing will be transferred to the inner one, and that way we can actually design it to have the minimum rotation on the outer footing. So we see how this can be done, and we have two footings, and these are the loads that are acting downwards, and the resistance that's acting, and depending on the size of this base, outer base, we'll have a certain eccentricity as well. And based on all these parameters, we can find the shear forces and bending moments that are acting on the strap beam. And also, in addition to that, what is going to happen to the footing. So last time we briefly discussed these equations, and this particular, so if you want to design this strap footing, we need to find the values of R1 and R2. Because P1 and P2 are known, they are known at the service conditions, so we can actually find the P1 and P2 at ultimate limit state as well, so that we can find the bending moments and shear forces as ultimate values on the connecting beam. So when P1 and P2 are known, and also when eccentricity has been selected, then we can find the corresponding values for R1 and R2. So there can be so many different solutions. So you have to select something reasonable for the eccentricity, which will finally decide the size of this particular outer footing. So with an example, we'll see how to handle this. And when you know R1 and R2, we know the pressures acting from below on both these footings. And if you know the vertical force and the pressure acting from below, it's possible for us to draw a bending moment and shear force diagram. And when the bending moments and shear force diagrams are available, we can decide the tension reinforcement requirement in the footings. And in this particular case, because this outer footing is trying to rotate outwards, you will find that due to the strap beam, there will be tension at the top surface of this footing. The reason is this is trying to move outwards, which means this will go into tension at the top surface. So if first task is to find R1 and R2, and you can see in this particular diagram, the distance S is known, and if we have a value for eccentricity, P1 and P2 are also known, then we can find R1 and R2. So R1 is equal to, we know the value of P, we know the distance, we know the eccentricity can be found. Similarly, R2 also can be found when P1 and P2 both are known, S and E are also known. So which means we can find R1 and R2. And when you consider the equilibrium of the whole system, P1 plus P2 should be equal to R1 plus R2. So how we deal with this is, first we have to look at the loads that are acting on the, footings. So we have to look at the loads that are acting on the footing and select a suitable width for the foundation. It is not necessary to have the same width for both foundations, but you know, if you have the same width, then it will be a little easier to do the calculation. So we see that if possible, we will go for the same width, and we can adjust the length to suit the selected width. The other option is, you know, have different widths for two footings. That's also possible. But for the example, we'll select a situation where we are going for the same width. So the other important thing that you have to see here is that you have the value of P1 and R1 will be bigger than that. And here you have a value of P2, R2 will be slightly lower than P2. So certain load transfer would take place due to the connecting beam. So what you do is, first we will find the suitable width, initial width for the foundation, and based on the initial width we can find a suitable length for this foundation. That means we can find a suitable length for this foundation. And when you know the overall length of the foundation, because we know this particular force is acting at the center, we can find the value of eccentricity. So once the eccentricity is selected, a reasonable value, we can actually select R1 and R2. From that point onwards, we will be able to select many other parameters that are unknown. So that's how we are going to attend the problem. The steps are given here, but we look at the steps by using an example. So initially you have P1 and P2, and we have already selected an eccentricity. And so we know R1 and R2, and because we are assuming that there is no rotation in each foundation, then we can assume a uniform pressure distribution under the foundation. And with a uniform pressure distribution under the foundation at ultimate state, and these loads also known, the distances are known, we can draw the shear force diagram. We can draw the shear force diagram by considering clockwise shear is positive, anti-clockwise shear is negative. Clockwise shear is positive, anti-clockwise shear is negative. For example, the shear at this particular phase is mainly due to this. And if this distance is the column size divided by 2, the shear force will be this value multiplied by this distance will give the shear force. And then we have to deduct that this reaction or this column load from that value of shear force. So we get a shear force on the right hand side of the column here. And then you can see, due to the load system on the base, this shear force will again start increasing, and it will go to another positive value. And between these two, we consider that the column loads are significantly larger than the weight of the beam. So generally what we do is we ignore the weight of the strap beam, because you know the column loads would be much higher than the the effect of strap beam. So if you want, you can simply ignore the weight of the strap beam. It will be only a very small contribution. So which means if you are ignoring the weight of the strap beam, the shear will not change from here to here. And then again, you can see some clockwise shear is acting. So this will start increasing again, go to a high value and then come. Which means some of these shear forces will be acting on the footing. Some of these shear forces will be acting on both the beam and the footing. And some of these shear forces can act only on the beam. So we have identified different situations. But you can see when you consider the beam, the shear force is not a very high value on the beam. The reason is, the shear force peak values are here and here, which are actually occurring in the areas where the footings are available. So if you look at this beam, it may not be subjected to very high shear, but the bending moment can be substantial. So then you can draw the bending moment diagram, and bending moment diagram is drawn on the positive side or the tension side. It is drawn on the tension side. The bending moment is considered as positive in the clockwise direction and negative in the anti-clockwise direction. And it is also considered as the bending moment diagram is drawn on the tension side, or the positive value is taken on the tension side. And if you look at this footing, it's going to bend this way, which means the tension side occurs here. So you can see the bending moment diagram has been drawn and below, and then it goes this way, come to a highest value here. When the shear force is 0, bending moment is highest. Come to a value, highest value somewhere here, which means the footing is also now subjected to some tension. And then it will start decreasing. And beyond this point, we have only the strap beam. So we design the strap beam for the bending moment here. We design the footing for the bending moment that occurs somewhere here with the maximum value. So we design the footing here. And when it comes to this footing, again, here you get a lesser bending moment. So this has to be designed for that particular value. And you can, when you look at the bending shape of the bending moment diagram, you can see, strap beam need not be of constant depth. It can be of variable depth as well, because the bending moment is reducing as it comes here. So if you want, you can have the smaller cross sections here for the strap beam, and then it goes to a value which corresponds to the bending moment that occurs on this side, and then finally it will come to 0. So we have to select all these values, the bending moments and shear forces, and once we do that, it's possible for us to find the reinforcement to resist flexure. And also we have to check for shear, which is the vertical shear and the partial shear. So if you look at this situation, there's a possibility for some punch and shear failure in this heavily loaded column if the thicknesses are the same. So you may have to look for punch and shear and direct shear failures, and select a thickness for the footing so that this direct shear failure can be withstood only with the use of concrete, without using any reinforcement. So let's look at an example. Any question you want to ask? So design example, design a strap footing for the column arrangement shown with the given permanent and variable loads. The allowable bearing capacity of the soil has been estimated as 170 kilonewtons per meter squared. And so basically, when you are designing the reinforced concrete system, we ignore the weight of the base. So when the allowable bearing pressure is 170, we can use a net bearing pressure of around 150-155 kilonewtons per meter squared, and that will all depend on the thickness of the base that you are going to use. And so the thickness of the base we have to estimate based on the shear failure. So we can first see the size of the base on plan. And based on that, we can decide whether the punchy shear failure is going to be a critical one or not. And also, based on the direct shear and punchy shear situations, we can select a suitable thickness for the base. So we have the two columns 6.2 meter apart. And one of the main uses of step beam is, when the distance between the two columns are high. If they are very low, then it's you can easily connect the two footings and design it as a combined footing. But if the columns are little apart, and combining the foundation may not be that economical, then the step beam can become a very good solution. And the column sizes are 400 by 400, and so if you want, you can select the same thickness for the step beam. On the other hand, you can even select 450 millimeter for the step beam, so that the steel in the step beam can be arranged on either side of the column reinforcement. Otherwise, what happens is, you have to use different cover values for the step beam and the column, because these reinforcement will be clashing each other. So it may be a good practice to select a width which is higher than the width of the column. So if you look at the loading condition, we have permanent load of 320 to 160 variable on this particular footing, that is the outer footing. And the inner footing is more heavily loaded, and it's logical because, inner columns generally tend to carry higher load because the contribution comes from all directions. Whereas the contribution will come only from the part of the structure on this side. So because of that reason, these loads will generally be less than the loads given here. So because, we have to do the step beam design under ultimate conditions, it's good to know about the ultimate the pressure distribution corresponding to the ultimate loads. So what we can do is we can find P1 and P2 values. P1 is the column load here, P2 is the column load here. So P1 will be 320 into 1.35 plus 260 into 1.5. So 1.35 times 320 plus 1.5 times 260. And similarly, we can find the ultimate load on the inner column, and that is 1,275 kilonewtons. And we can also find the service conditions, and the loads that are transferred under service conditions will be the addition of all these loads. So which comes to 320 plus 260 plus 500 plus 400, 1480 kilonewtons. And that is the total service load. And these two are the ultimate. So if you want, you can find the ratio. Ultimate ratio RU is equal to the addition of these two divided by the addition of all the dead and live loads, 1480, and you will get an answer of 1.42. So if you have gone for a very marginal case where the soil pressure under these footings will be 150, that means then the ultimate pressure that is applied from below will be 213 kilonewtons per meter squared. And you also know the average, the allowable bearing capacity is 170. And we, after allowing for the weight of the base, we actually went with 150. And once you multiply 150 by the ratio between the ultimate loads and the service loads, you can find the ultimate pressure we can expect under the foundation. So we can expect an ultimate pressure of about 213 kilonewtons per meter squared that will act from below. So then we'll also look at the total load acting here, and it's about 900 kilonewtons, and we know that load will be reduced slightly due to the strap beam. So if we consider that this particular load is acting, and the addition of those two loads will be 900 kilonewtons, and 900 divided by 150, we'll get 6 square meters. And if you take the square root of that value, then you will end up with a base size of 2.4 meters by 2.4 meters. So if we assume that the load acting on this particular base is about 900 kilonewtons, and we have a net bearing pressure of 150, from that we can find the corresponding area is 900 divided by 150, which is equal to 6. And if you take the square root of 6, then you will find it's about 2.44. So that means, if you are going with a square base, we will need something like 2.44 meters, 2.44 meters by 2.44 meters. So based on all this, let's consider that, a reasonable value for the width of the base may be 2.5 meters. 2.5 meters, because when you divide 900 by 150, the answer is 6, and when you take the square root of that, you will end up with 2.44. So let's select 2.5 meters as the width of the base. So if you have an approximate value for the width of the base that you have already selected based on some trial calculation, then we can also find a reasonable value for the size of this base, and the addition of the load on this base is 320 plus 260, that is about 580 kilonewtons, and and we know it's going to increase. So if we divide 580 by 150 divided by 2.5, so we get something like 1.54 meters. And because we know the load will be higher, so let's select something like 1.8 meters for the width of this base, for the length of this base. For the length of this base, let's select a value of something like 1.8 meters. So if you select 1.8 meters, then from the center it's 0.9 meters. Size of the column is 400 by 400, which means from the center line you get 200 millimeters. If this width is 1.8 meters, then you will get the center line here at 0.9 meters. 0.9 minus 0.2 is equal to 0.7 meters. So, moment you select some approximate values for the bases, these are not finalized yet, but we have some idea that an eccentricity around 0.7 may work, which means an eccentricity of about 0.6 also might work. So let's start with an eccentricity of 0.7, and if it gives reasonable values, we can stop the calculation. Otherwise, we'll have to do another trial. So, but we have not arbitrarily selected these values. We looked at the bearing pressures, and then we decided that a width of about 2.5 meters is what we like to have. And also we considered that the load on this footing can be higher than the addition of these two. So based on the width and the allowable bearing pressure of 150 and these two loads known, we can calculate an approximate value for this dimension, which came as 1.54 meters. And knowing that the actual pressure that will be acting from here will be more than this, we select a slightly higher value. So I have selected 1.8 meters. Is that clear? Can somebody give some feedback? So we had to first select some dimensions for the footing, because they are not given. And I have selected a value like 1.8 meters based on some trial calculation, where I took into the consideration the loads acting here and the fact that the loads can be higher than the addition of these two under service conditions. So based on all this, and that is the description given here, based on all this, let's consider that we are going to consider a length of 1.8 meters, giving an eccentricity of 0.7 meters. So if you look at the theory, and you see when P1 and P2 are known at ultimate state, the distance between the centers are also known, that is S, and the eccentricity is known, then it's possible to find the values of R1 and R2. So first we'll find the value of R1. So the value of R1 will be 822, that is this value for P1, multiplied by 6.2 meters, divided by 6.2 minus 0.7, eccentricity is 0.7, distance is 6.2, you get 927. So you can see you get an increase in the outer footing axial force or the vertical force. And so we have to resist this much of vertical force. And then R2 also can be found similarly by taking moments about R1. And we are just substituting in this equation, which is already derived. So just substitute these two values, and this is 6.2, this is 0.7. So you can see you are ending up with a slightly lower value than the load on than P2. P2 is 1275, whereas the R2 value is 1170. So what we can do is select a thickness, select a length of 1.8 meters, width of 2.5 meters for this, and then see what is the soil pressure that will be acting on this. And we have to make sure it's not excessive. So now you know the value of R1, which represents the soil pressure, is 927. 927 divided by 150 divided by 2.5, and we'll get a value of 2.47 meters. Oh, sorry, this 927 is as an ultimate value. So 927 divided by 213. So we are divided by 213 divided by 2.5. We get a value of 1.74 meters. So which means, you know, the value we selected as 1.8 meters may be okay. So based on this 1.8 meters and 2.5 meters, we are not exceeding the bearing capacity. So we can actually select the pressure that is going to act from below. So we have a footing of 2.5 meters of width, 1.8 meters of length, supporting an ultimate load of 900, ultimate pressure of 927. So we can divide 927 by 1.8 divided by 2.5. So you'll see that, you know, the vertical pressure that we can expect from below is 206. And if that value is less than this 213, that corresponds to the maximum pressure that we can exert on this particular soil. So because we consider the net bearing capacity of 150, and once you multiply it by the ultimate factor, you get 213 kilonewtons per meter squared, but due to this R1, we are getting a value slightly lower than this. So which means, you know, the under the footing, the allowable bearing pressure will not be exceeded. So we have got a pressure of 206 kilonewtons per meter squared, and we'll use that value. We'll use the same value and a width of 2.5 meters for this base, and then we can find the length of this base required. Then we can find the length of this base required, that is the inner base. So outer base is 1.8 meters of length and 2.5 meters of width. We know this is going to be 2.5 meters of width, and we also know the bearing, ultimate bearing here 206. So we can say we are going to maintain the same ultimate bearing here as well, again 206. And corresponding to all these, we can find a suitable width for this inner footing. So inner footing loads are known, pressure is known, then we can find a suitable width for this base. So that is the other unknown parameter. Width is 2.5 meters. We can find a suitable length for this base. So you can see the bearing pressure is 206. So the length of the inner footing will be 1170 divided by 206. 206 divided by 2.5. And that gives a value of 2.27 meters, and we select 2.3 meters as the length of this base. So this base has a length of 2.3 meters. This has a length of 1.8 meters. The width is the same, 2.5 meters. So that, which means we have selected almost all the parameters, including the eccentricity value E, which is 0.7 meters. So we have a distance of 6.2 meters and a total load of 822 acting here, a total load of 1275 acting here, and these are due to ultimate. And also, in addition to that, we are having an upward soil pressure of 206, and we have to multiply it by the width of the base, then then we can get it as a line load. So basically we are having a line load of 515 kilonewtons per meter. So we have considered that due to the way that we selected, the size of the bases, the pressure here will be 206, here the pressure here also 206, the width of the base is 2.5 meters. Then we can see this line load should be 515 kilonewtons per meter. This line load should be 515 kilonewtons per meter. And that is in equilibrium with the stiffness of this trap beam and P1, P2 and any pressure that will act here. Again, we know we have arranged it in such a way that will also be 206, almost 206 kilonewtons per meter. Is this clear? How to select the size of the bases? So the task is first select the suitable size for the outer base. And based on that, select the select the corresponding value for E, and then find R1 and R2, and based on R1, see whether the allowable pressure is exceeded. If it is not exceeded, you can stay with the dimensions you have already selected, 1.8 meter by 2.5 meter, and then we have to find the suitable size for this base. We know the width is 2.5, and then from below we get a force of 1170, and also we like to have the pressure underneath this to be equivalent to 206. So we can find the length of this, and then we can complete this line force diagram where these forces are concentrated forces and these forces are considered as distributed due to the fact that bases are resting on the ground. The bases are resting on the ground, so you get pressures, and these can be different as well, but we are selected in such a way they are equal because we want to come closer to the maximum pressure that will be allowed, which is 150 net this case. So when you know this diagram, I'll make it smaller so that you can see it. And here you can easily draw the shear force diagram, which is 515 into 0.2. 515 into 0.2 is 103, and 103 minus 822 is 719, and 719 again this will go in the same gradient of the slope, and so the value here will be minus 719 plus, here you can see these clockwise shear, it's positive, and the value here will be the 719 minus whatever the shear that is acting upwards. So which will be equal to minus 719 plus 515 into 1.6. So you get 105 as the answer. So here you get 105, it does not change. And here again it will start rising up to the center line. And the value at the center line will be 105 plus 515 multiplied by 1.15 meters. Because here you can see 2.3 meters, so half of that is 1.15 meters. And you will end up with a value of 697, and then due to the action of P2, which is 1275, you will get another negative region, and then when you add the clockwise shear in this area, finally you will end up with C. So this way you can draw the shear force diagram, And in this shear force diagram, this particular point is an important one because it shows us the place where the bending moment will be maximum. So the bending moment will be maximum here, and to find this particular distance, we know this is 719 and we know this line load is 515 kilonewtons per meter. So what we can do is, if we divide 719 by 515, we can find this length. We can find this length. So basically minus 719 plus 515 into 1.39 is minus 719 plus 515 into 1.39 is 0. Yes, it comes to 0, almost 0. So this way you can actually select this point, and then if you take moments about this particular point, then you can find the maximum bending moment on the outer footing. So what you can do is, to find the bending moment here, you can find the bending moment here, which is 515 multiplied by 0.2 multiplied by 0.1. Sorry, 515 multiplied by 0.2 square divided by 2. Point 2 multiplied by 0.1. It's 10.3. This should be 10.3. So the bending moment here is very small, which is only 10.3. And then you can take the bending moment about this point. So that's the point where the shear force is 0. The bending moment here will be, this is 1.39, this is 0.2 meters. So the bending moment here will be 515 multiplied by 1.59 multiplied by 1.59 divided by 2 minus 822 multiplied by 1.39. So when you do that, you get minus 192. And then similarly, you can take moments about this point, which is equal to 515 into 1.8 square divided by 2 minus 822 into 1.6. And as given here, you can see the bending moment here is 480. And then you can take the bending moment about this point, which is equal to 515 into 1.8 into this particular distance, that is 3.45 plus 0.9 minus 822 multiplied by 3.45 plus 1.6. So you'll end up with the answer of 118. And then if you want the bending moment here, you can consider the right hand side and consider the bending moment. When you consider the right hand side and take the moment, you will end up with the answer of 340 kilonewton meters. So here you get 340, 118, and so all these values are known, which means we are in a position to now decide the reinforcement requirement in the strap footing. And we can also see whether the shear is going to be critical or not. But to do all these things, because the bending moment diagram is known, we have to think about a suitable size for this strap footing, strap beam. We have to select a suitable depth for the beam. So how to select a suitable depth for the beam? We can make use of this particular bending moment of 480 that is acting on the beam to select a suitable size. And to select the suitable size, what we can do is, we know the bending moment. We can, let's assume we are using 25 megapascal concrete, and we like to use the same width as the columns for the strap beam, which is 400. If you want, you can go for 450 as well, considering that the reinforcement can be fixed easily. So this width is also known. Then we can say MO FCK BD squared. We can select a suitable value, and we know the maximum value for singly reinforced case is 0.167. So I have selected 0.07. I could have easily selected 0.09 or 1, but I selected a low value to ensure that we'll end up with a reasonably deep beam. So if you select a suitable value for this, then you can find a corresponding D value. And once you know the effective depth, you can work out the actual depth of the beam. So effective depth needed is about 828. So let's select a depth of 900 millimeters for the beam. And when you are selecting the size of the strap beam, don't select a too small depth, because the effectiveness will be less. One of the important things is the stiffness of the beam. So because of that, I have not gone for value close to 0.16. I've stayed somewhere here and ended up with a 900 deep beam. And once I know the depth of the beam for 480 kilonewton meter moment, I can work out the reinforcement requirement. And the reinforcement requirement can be found once you decide the value of Z. Z is 0.935D, is the usual equation we use. And once you know the value of Z, we can find the reinforcement requirement because the bending moment is known. So bending moment is 480, and we have found the reinforcement requirement as 5 numbers of H20 bars, or 1405 millimeters squared. So basically, you can see that for a 900 millimeter deep beam with 5 numbers of H20 bars as the top reinforcement, you can design this beam, and the strap beam is not subjected to any sagging moment; it's subjected to hogging moment. So you can provide some hanger bars at the bottom of the beam. But when you are providing reinforcement at the bottom of the beam, you have to consider the fact that between the two footings, the beam is not supported by anything. So if you are going to have a ground slab supported on the strap beam, then you have to design the strap beam for a sagging moment, which will come due to the weight of the ground slab. So you might have to consider the fact that this beam can bend this way as well if there's a ground slab supported on the strap beam. So once you know the reinforcement, you can also look at the shear, and these areas, the chances for shear failure would be remote in the strap beam because it's supported by the footing. So what you have to see is whether the shear failure can occur somewhere here, and here you can see the shear force is 105, and if you look at the shear stress, 105 divided by 400 divided by 840, you can see the shear stress is 0.312, which is actually lower than the shear carrying capacity of concrete, because generally we know the shear carrying capacity of concrete is around 0.35 and above, 0.35, 0.36 and above. And the shear stress we get is only about 0.31, which means the shear stress is very low, which means, you know, we might be able to just provide nominal links. So, or the minimum links, we'll be able to provide the minimum links in the beam. And then for the selected minimum reinforcement, the minimum links, we can find the shear resistance. And if that shear resistance is more than this, then the strap beam will be okay. And we can also select this region. And you can see in this region, it is pretty close to the column face. And the critical section will be D away from the column face. And then we are again coming pretty close to this value. So which means the strap beam might need only the nominal reinforcement when it comes to shear, or the minimum reinforcement when it comes to shear. So shear is not a critical issue. Then the other issue that we have to consider is, what are we going to do with this 492 kilonewton meter moment? And that 492 kilonewton meter moment will act on this base. So which means we'll have to select a suitable thickness for this base. And how do you select the thickness for this base? So when it comes to the selection of the thickness, we know a load of the pressure of 206 kilonewtons per meter squared is acting upwards. And then we have selected a width of 2.5 meters. That means, you know, we are getting a projection of 1.25 meters from one side. And then when you deduct half the column size, which is 0.2 meters, we'll have about 1.05 meter cantilevering from the face of the column. And then when you look at shear, we have to select the shear. We have to check for direct shear at a D away from the face of the column. So for that, we have to select a suitable value for D. So when you consider the size of the footing, 2.5 meter by 2.3 meter, it may be reasonable to you select at least 0.5 meters or 0.6 meters for the thickness. And once you select a value of our thickness, let's say we select 0.6 meters, then we can work out the direct shear and check for the direct shear force. And if the direct shear is okay, then we don't have to worry about it. And also, so once you know the thickness of this base, let's say 0.6 meters, and we have a bending moment of 492 acting on this way, and which means, you know, it's kind of hogging. So we need top steel in the footing one. So here we have to provide some top steel, and this top steel can be found to resist this bending moment. And you know that, you know, this particular bending moment acts here somewhere close to this. So this particular reinforcement may need to be bent downwards and anchored, because generally we say the reinforcement should be continuous, at least an anchorage length from the critical section. So generally the critical section occurs somewhere here, but in this particular case, the critical section occurs here. That means this reinforcement may need to be bent downwards and anchored inside the footing. So you have to select a reasonable thickness for the footing. It can be about 0.5 to 0.6 meters, considering the size of the footing. And then you have to decide the amount of reinforcement needed. And because the width of the base is 2.5 meters, again you can concentrate most of this reinforcement close to the close to the column. We discussed it last time. We said that, you know, column plus 3D rule. So we can have a concentration of reinforcement close to the column as well. So if you consider the footing, you have to consider the direct shear failure in the width direction, not the length direction, because width is more than the length. And then we also need to know whether the punchy shear failure can occur here. And for punchy shear failure, we can select a punchy shear perimeter, maybe 2D away, and that is the normal perimeter that we generally consider. But if you consider a thickness of 0.6 meters, then 2D, 2 times D will be something like 1 meter, and the projection is 1.25 meter. Then you will find that the punchy shear perimeter will come almost close to the perimeter of the footing. So punchy shear may not be that critical, but you can also check punchy shear within D to 2D to make sure this heavily loaded footing is safe in punchy shear. Because in footings, you have to check punchy shear not only at 2D from the face of the column, but you have to also check punchy shear within D and 2D. Within D and 2D, also we have to check punchy shear. So this might need punchy shear check because it's a more heavily loaded footing. So those are the checks you have to do. You have to check for punchy shear, direct shear, and also decide the flexural reinforcement. So the flexural reinforcement of this footing will be designed for this pressure. And in addition to that, you will have to consider the transverse reinforcement in this footing as well as this footing, and that reinforcement has to be decided by considering a face here. So the transverse reinforcement on both footings have to be considered by considering a critical section here. So that way, you know, you can decide on the bottom reinforcement of this footing. And in addition to that, this footing will need top reinforcement as well. This footing will need mostly the bottom reinforcement. But because these are important structural system, if you want, you can provide some nominal reinforcement at the top of this footing. And this way, the bending moment is not that critical because this footing is supported by the strap footing. So this direction at the bottom, you will be able to provide nominal reinforcement. So if you consider this particular footing, there will be a main reinforcement this way, a nominal reinforcement this way at top, main reinforcement this way, and nominal reinforcement this way, main reinforcement this way, and nominal reinforcement this way at the bottom, and this will have the main reinforcement this way as well as this way at the bottom, and in the top, if you want, you can provide some nominal reinforcement. And in addition to that, there will be top reinforcement in the strap footing, a strap beam, and some reinforcement here if it can be loaded downwards. And then you have to also check for shear. It looks like shear is not that critical in the strap beam, but you have to check the direct shear here, and you also have to check direct shear here. And in addition to that, you can check this for punching shear because this footing is going to be the more heavily loaded footing. So those are the checks you have to perform, and then you can decide on the reinforcement requirement. So any questions on this? So any questions on this? Indranil, are you there?
Yes, sir.
Is it you could understand it, or you have any questions?
Yes, sir. Could you explain again that selecting nominal reinforcement in the top of
Nominal reinforcement in the base. Is that right?
Yes, sir. Base.
Yeah. Now, if you look at this particular base, now if you look at the loading system, you can see the loading system is, it's loaded from below. So you get 206 acting here, right? So you get 206 acting here. So which means this can bend upwards. So we need main reinforcement here, this way, because it can bend upwards here, because there's a projection, and that projection is subjected to 206 kilonewtons per meter squared from the strap beam, face. So from the face of the strap beam, it's subjected to 206 kilonewtons per meter squared. So that means, you will get a bending moment here at this location. So you have to provide main reinforcement this way. But due to the strap beam, you can see, it cannot bend in the other direction. So you have to provide nominal reinforcement this way. You have to provide nominal reinforcement this way at the bottom. Then due to if you look at the bending moment diagram, it's going to bend this way. The footing is going to bend this way at the top. So that means, you have to provide top reinforcement to resist that. You have to provide top reinforcement to resist that. And then you have to provide nominal reinforcement this way, because when you have top reinforcement here, you need some nominal reinforcement this way. So you have to provide minimum reinforcement in this direction. When it comes to this footing, you can see you can have a critical section here, this way, and you can have a critical section this way, and you can have a critical section this way. So that means this footing will need main reinforcement in both directions. Main reinforcement in both directions. And in addition to that, you can check this for punching shear and direct shear. And so if this is okay, the likelihood is this also may be okay, because the pressures are the same. So if this is okay with direct shear, this also will be okay with direct shear. Is that clear, Indranil?
Yes, sir. Clear.
So you have to look at the total force system, because we have a force system acting from downwards, in the upward direction. In addition to that, we get a bending moment transfer through the strap beam, and that is due to preventing the rotation of the footing. Anybody else having any question? Then shall I end and give you about 10 minutes break and start at 3:20?